So for today, it will be our second class, and we will still look at the theory that is being used for our simulation. So it's important that we go through the theory. I understand some students have expressed to me that it is very difficult, but I think the approach here in this class is that the focus is on applying these theories in our simulation. So it's important that you understand so that you do not make so you understand what you are doing. And I think most of you from UTM, you have attended the class for quantum chemistry, so you have the basics actually. So it's just a run through, an overall summary of what you have learned, but it has been made into a very simple context, and so that you can understand. All right. So Dr. Fadilla has done a very good job in doing that. So, however, today he's not here with us because he's attending a workshop. So he has actually instructed Rizka, his student. She's currently doing her PhD in Osaka University, under the supervision of Prof. Morikawa. Am I right?
Yes.
Yes. So thank you for joining us today and helping to deliver the lecture. So I hope every one of you have downloaded your lectures, your lecture notes, okay, gone through them. We also have exercises, so please pay attention during the class. If you have any question, you can also ask, unmute your mic, and you can ask the questions. We have breaks in between, since it's 2.5 hours. So we have breaks in between. And please answer the questions, and we will have to submit it before Maghrib. Okay? You have to submit it into the e-learning in UTM. All right, for UTM, and all for the respective universities, you will submit to your respective e-learnings. Okay. So don't worry about the answers. Try your best to answer them. Okay, you are free to use the Google the answers, or just to find out. Okay, to read about it. Okay, don't just copy paste. Try to read about it, and we would. The most important thing is that you have to submit on time. All right. We will grade you. So those who submit late, we will deduct marks. Okay. And I know some of you, for last week's exercise, I have to remind you to submit. Yeah. So please do not be late. Okay. We will grade you. All right. Okay. I think, is there anything else you'd like to add, Dr. Vera?
No, I think it's enough, Dr.
Enough. Okay. Okay. So I think we shall begin. All right. Thank you, Rizka.
Sure. I'll try to share my screen.
Yeah. Oh, sorry. Am I sharing or no?
No. So, can you see my screen?
Yes, I can see your screen.
And what about my voice? Is it clear enough?
It's clear. Very clear.
Okay. So, let me start. Today, we are in our second meeting of the molecular physics and material science in the framework of first principle methods. So,
sorry, is it recording? Are we recording now? Oh, yes.
Is it recording already, Dr. Mark?
I'm not sure who's the admin.
What about the admin?
Yeah, I think it's recording.
It's recording.
All right.
Okay. So we are in our second meeting for the course Molecular Physics and Material Science in the framework of first principle methods. And last week, we learned about the general electron theory, and today we will learn about the density functional theory. But before that, please let me introduce myself again. So my name is Rizka Nur Fadilla. This is my name. You can call me Rizka. And I'm a student of Febian Sensei since I was in undergraduate school in Universitas Airlangga. And then Febian Sensei sent me to Osaka University to pursue my PhD. And now I'm in my third year under the supervision of Morikawa Sensei, Yasitada Morikawa Sensei. So as Dr. Mark has said, that today Dr. Febian is having an assessment outside Surabaya. It is an assessment for book editor certification. So that's why Febian Sensei could not attend here. And today I will be the one who introduce about density functional theory. So our goal today is to understand the basic density functional theory and its application through Kunsham's equation. And to achieve the goal, here is our today's menu. So we have 6 parts. We'll start with the time-independent Schrödinger equation, briefly on electron theory, hydrogen atom, many electron system, and then density functional, DFT in action, and closing. So as Dr. Mark has said, this topic, these materials may be rather heavy because we may see some equations or mathematical things, but we don't need to worry. For the moment, maybe we can just take it for granted. And later, if we already try to do the practice and then we get some problems, we can take a look back some of these parts to get a deeper understanding. So for the moment, don't worry. Just try to follow as best as you can. So now let's start to talk about the first part, the time-independent Schrödinger equation, briefly on electron theory. So this is a review of what we have learned in the previous meeting. First, electrons make material can reflect light, which is the electron-light interactions. And then electrons are either inside the material, like atom, molecule, crystal, or anything else, or it is wandering in the space as a free particle. And then the motion of electrons in the material govern all the properties of the material. And engineering the motion may change the properties of the material. If we want to understand the motion of the electrons, we need to use quantum mechanics approach in which we apply the wave equation of motion for the electrons. And the wave equation of motion for the electrons is the famous Schrödinger equation. According to the Schrödinger equation, the engineering of the motion can be done by changing the potential energy. So before we engineering anything, we have to know how to calculate the wave function of electrons. And the wave function of electrons is the solution of the Schrödinger equation. This is a famous equation. And it is represented by equation number 1. So for today's material, I will try to go as slowly as possible so that everyone can follow. In the first equation, we have minus h bar over 2m. And then we have the partial derivative, second partial derivative of psi plus Vx multiplied by psi as a function of t and x. T represents time and x is the position, which is equal to I, h bar, and the derivative of psi, the first derivative of psi. And the potential energy function, V as a function of x, and maybe for the next I will read it as Vx, is always time independent. It is time independent because we don't have t here. We only have x, which is the position. And therefore, we can simplify equation 1, this equation 1, to time independent Schrödinger equation or TC. So equation number 1 is still time dependent, and then we transform it into time independent Schrödinger equation, which is equation 2. Now, let's take a look what is changing from equation 1 to equation 2. The black part is still the same. We have minus h bar squared over 2m, but the second part is slightly changing. And in equation 1, we have the partial derivative. So you see this dou symbol, dou sign. And then in the second equation, we have d. So it is just ordinary derivative. And then in the first equation, we have this, let's say, big psi. But in the second equation, we have small psi. And then Vx is still the same, it does not change. and psi, big psi is changed from tx. So originally it is a function of time and position, and now it is only depends on the position. That's why it is time independent Schrodinger equation. And it is equal to E multiplied by psi again, small psi. So now the solution, which is this psi, this red one, is time independent. But wave function, it must be time dependent, right? And the answer is yes. But don't worry, if we have the psi x, this is the time independent one, we still can form the big psi, the wave function, the time dependent wave function, by multiplying the psi, which only depend on x, by exponential minus I e divided by h bar multiplied by t. So this psi, this big psi, the time dependent one is the wave function. And this small psi, it is called as the portrait of wave function. So I repeat again, this big psi is the wave function, but this small psi is the portrait of the wave function. So now let me tell you about what is portrait of wave function. And to do that, we can pay attention to this figure. And in this figure, we have a rope here. This is a rope. And then we also see a cat. And then this cat's name is Muharram Kifli, and we usually call him as Hara. And as you know, guys, he is very famous because he already appeared as a cover boy in one of Webb Janssen's book with the title of Quantum Physics. So he is already famous enough, more famous than me. So because Hara is already very famous, for this course, instead of Hara, it will be Aksa Nur Hasana that will be the actress along during the course. So we will often to listen to Aksa's wisdom. And anyway, let's go back again to the portrait of a function. In this figure, we have the robe and we also have Hara, Muharram Kifli. So if you look into the figure, do you think that Muharram Kifli stays still when the picture is taken? And I believe you think that when the picture is taken, Hara is moving and the rope is also moving, even though from this picture, both are standing still. And that is actually the concept of the portrait of the wave function. The wave function itself is actually moving, but the portrait of the wave function, which is the psi x, is a picture of wave taken at a certain time. So it is only take at a very particular time. That's why we call it as portrait of wave function instead of the wave function. So I hope you already catch the difference between the wave function and portrait of wave function. Now, let us listen to what Aksa is going to say. So this is the time-independent Schrodinger equation, equation 2, we see in the previous slide. And she said, the reason we keep seeing this scary equation is that it is the central of the electron theory. But it won't be long, and soon we will never see it again. I promise. Therefore, be patient, my followers. So this is not me who mentioned this promise. It is Aksa instead. So if anything goes wrong, if you still see this scary equation, please don't blame me. Just blame Aksa if you dare. All right, we already done with the first menu. And now we will start the second menu, which is the hydrogen atom. So maybe before moving to each menu, I will give 1 or 2 minute breaks to relax a bit because the material is rather heavy. Is it all right, Dr. Mark and Dr. Vera?
I think I can continue. What do you think? We have just started, actually.
Oh,
So we are
okay.
still fresh. I
So
think
still
we
fresh?
can,
Okay.
yeah, we can still continue. Maybe after hydrogen atom, we can have a break.
Okay, okay.
Okay.
So let's get ready to the next part, the hydrogen atom. So previously, we already see equation 2, exactly this equation, the time-independent Schrödinger equation. And according to AXA, this equation is for one electron or one electron Tc. So I asked AXA, and how do AXA know that it is for one electron? And the answer is that because there is only one m. So you see in this equation, there is only one m, which means it is for one electron. However, the solution, d psi x, may be more than one. And I asked AXA again, how come she did come with such conclusion? And she explained that both sin kx and cos kx are the solution from the same wave function. Furthermore, the linear combination of them, which is C1 sin kx plus C2 cos kx, are also the solution. And C1 and C2 here is just any coefficient or dynamic coefficients. And this concept is called as superposition. And the wave function from the Tc, the portrait wave function, behaves exactly the same. So this superposition, we will not talk about this further, but you have to be familiar with this kind of thing because you will have a question in the exercise about the superposition. So pay attention to what AXA has explained about the superposition. And then we are still seeing equation 2, the time-independent Schrödinger equation. And we realized that the psi is only a function of x. But in reality, any particle lives in three-dimensional space, such as in Cartesian coordinate, Cartesian space xyz, or the spherical space r, theta, phi. And since the particle lives in three dimensions, the position of the particle is identified by a position vector, which is denoted by this R with arrow on the top of it. So this arrow denotes that it is a vector. So this R vector is equal to xi hat plus yj hat and zk hat. So this ijk is the direction, the unit vector. And therefore, because the particle live in three-dimensional space, the function in equation 2, so we have this function, must be also in three-dimensional coordinate, which is x, y, z. And we can simplify it by writing it as function of vector r. And the consequence is that, so psi, we change psi from a function of x to a function of r. It means that the partial derivative here is also need to be changes. Originally, we only take the derivative with respect to x, but since we change it to three-dimensional space, now we need to take the derivative with respect to x, with respect to y, and also with respect to z. And that's why we have these rather complicated terms. And we can simplify it into this nabla square f. This is only to simplify this complex equation. If you don't really understand how this second partial derivative comes up, don't worry. Just take it for granted for the moment and we can come back later if it is needed. So now after we change it to three-dimensional space, and then we define a new symbol here, now we can rewrite the one electron 3D Tc like the following equation. So from equation 2 to this equation, it is similar. What is changing is only this partial derivative part and also the variable inside the function. And then we can factorize this by taking out the psi outside the bracket, so that we have a more simple equation, which is shown by equation 3. So now equation 3 is the TC, is our three-dimensional TC. All right, we already know the equation. Now we try to implement it on the case of hydrogen atom. So this is the real case. For the hydrogen atom, we have one nucleus and also one electron, right? And in this figure, the nucleus is represented by this red circle with label A. And the electron is represented by this blue dot with label 1. And the distance between the nucleus and the origin, it is denoted as RA. The distance between the electron from the origin is denoted by R1. And the distance between the nucleus and the electron is denoted by RA1. So see, A here refers to the nucleus and 1 refers to the label of the electron. Now let's write the TC explicitly. So this is our TC. If I go back again a bit in equation 3, you can see we have two terms inside the bracket, right? Two terms. This is 1 and this is 2. And here we also have two terms. The first one and the second one. And then let's go deeper slowly on each term. So first here we have E. E is the charge of the nucleus, this nucleus A. So we know that nucleus is positively charged. That's why we have positive sign. We don't put it explicitly, but this is positive E. And then for electron, the charge is also E. We only have one electron, and the sign is negative because it is electron. So negatively charged. And then the term inside this circle, it is the electrostatic potential field generated by nucleus A. So this nucleus generated a electrostatic potential field, and it is felt by electron 1. And this is the mathematical expression for it. And this electrostatic potential rises a so-called central force. So if you don't know what is central force, you have to look it up by yourself. You can find it in Wikipedia, Googling, or ask ChatGPT or any other resource. So anytime you find this, what is it called? Magnifier symbol, you have to look for the term by yourself, because maybe it appears in the questions in the exercise. So that's why you have to look it up. And then here we have E. E is a total energy, which is the summation of the kinetic and also potential. So here we have kinetic and also potential. Now we discuss the first term, this part. It is called as a one electron kinetic operator, or denoted as T0. So we know that kinetic operator is to measure the energy of any particle which is moving. So every object that is moved, it will always have kinetic energy, and it is measured by the kinetic operator. But this is not ordinary kinetic operator, it is one electron kinetic operator, which means this operator calculates the kinetic energy of the electrons without considering the presence of any other particle. So actually here we know that there is nucleus, right, inside the hydrogen atom, but this term calculates the kinetic energy of the electron that is moving without considering the presence of other particle, without interacting with other particle. So we can say that this electron is quite individualistic. So it just moves without interacting with anything else. That's why we call it as one electron kinetic operator. And then for the second part, we have this red part. We have the electrostatic potential operator, or denoted as VES. And from the term, we know that electrostatic, it assumes that both the nucleus and also the electrons are in static. That's why they are called electrostatic, because it assumes the particles are in static condition. So it assumes the nucleus and the electron are not moving. And by now you must be realized that there is a contradiction, right? In the first term, we measure the kinetic energy of the electrons, which means we assume the electron is moving. But for the potential, we use electrostatic potential, which assumes the nucleus as well as the electron is static. They are not moving. So you see the contradiction, right? The first term assume electron is moving. The second term assumes that the electron is static. So even though there is a contradiction here, but somehow this equation works. So you will see later. And then this equation, this is rather long. We don't like it. So it can be simplified into the one in the box. It is a simpler version on the one electron 3D PSA, which is T0 VES multiplied by psi equal to E multiplied by psi. So I believe you already know what is the paradox happen in the hydrogen atom case. And this is one of the question in the exercise. So I hope you can answer the exercise, because I already discussed a bit before about the paradox. So we already have this equation. Now our task, the next question is, what is the solution of this equation? And the solution is the orbitals and the energies. So we have two solutions, the orbitals and the energies. The orbital is represented by this psi. And this psi governs by three parameters, which is n, L, and m. And these numbers are the quantum numbers. N is the principal quantum number, L is the azimuth quantum number, and m is the magnetic quantum number. So this is the orbital. This is the first solution. And the second solution is energies, which is represented by this E. So we have energies. What energy it is? It is the energy of the orbital. So for example, the energies of the orbital, 1s orbital in hydrogen atom is minus 13.6. And then the energy of the 2s and 2 pi orbital is minus 3.4. But pay attention here, we have 2s, one type of 2s, but we have three types of 2p orbital, which is when m equal to 0, when m equal to +1, and also -1. So we have 4 orbital, 1 2s orbital, and 3 type of 2p orbital. And here we have 4 type of orbital with the same energy, which is minus 3.4. And this phenomenon is called as degeneracy. So degeneracy means we have a different type of orbitals, but the energies are the same, and it is called as degeneracy. We also observe it in the case of n equal to 3. We have one type of 3s, we have 3 type of 3p, and we have 5 type of 3d. We have d orbital for m equal to 0, +1, -1, +2, and -2. So in total, in this row, we have 5 plus 3, 8, +1, 9. 9 orbital have the same energy. And this energy is the functional of psi n. Remember psi n? And functional means function of function. So let me give example. Here we have psi r, this is a function, psi a function of r, because r here is a variable, that's ordinary variable. But but if we change r with a function, so r is actually variable, right? If we change it into a function, then it becomes functional. So functional is a function of function, which is denoted by this square bracket. And in this case, to calculate the En, we can use this equation. I'm sorry, we should have a negative sign here. It's a typo. Minus 13.6 over n squared EV. So in this case, when n is equal to 1, it is easy. It is just minus 13.6 divided by 1. We get minus 13.6. And for the case of n equal to 2, we need to divide minus 13.6 by 4. And we got 3 point something, 3.40. And the way this representation is called as energy level diagram. And we can also visualize the orbital. Previously, we see the orbitals in terms of energy. Now we can see the shape of the orbital. So this corresponds to S orbital, which is when L is equal to 0. Remember, this L is the quantum number. When L is equal to 1, when L is equal to, we have this d orbital. And then this is corresponds when M equal to 1. And then M prime, see, this is M prime, it is not M. M prime equal to plus 1, minus 1, plus 2, and minus 2. And we have to take note that this M prime, this is M prime, but this is M. So M prime is actually the linear combination of the original M. For example, for the case of M prime is equal to 1, which is px orbital, it is the combination of two terms. It is when equal to M is minus 1 and M equal to plus 1. And the question is why we have to take such linear combination, why we don't directly use the M? It is because other than M equal to 0, so if M is equal to 1, 2, or etc., they are a complex function, and complex functions contain imaginary part. And we need to get rid of the imaginary part so that we can plot it in the polar coordinate. Now, that's why we take the linear combination, because the original M have imaginary part, and that imaginary part make us cannot plot it in the polar coordinate. That's why we take the linear combination to get rid the imaginary part. And that's why maybe you often see the visualization of the orbital like this. And then now we have completed the first case, the hydrogen atom. Maybe we can take a 1 or 2 minute break. You can have some drinks. I will also drink.
Yes, sure. We'll take a short break.
Yeah.
Okay.
If you are getting confused in the middle of the way, you can take notes, and you can also ask maybe via Dr. Vera or Dr. Mark, and then we can review it later.
I have a question. Can we go
yes,
to
Dr.
slide 12?
12?
Slide 12.
This
All right,
one?
you mentioned about the potential, I mean the energy, the potential energy, 13.6 divided by n square,
Yes.
right? So
this one?
how do you get the energy for 2s and 2p orbitals?
This one?
Yeah.
Yeah, in the case of the hydrogen atom, it only depends on n.
Yeah.
Yes, so
there's only one.
that's why we only, for 2s and 2p, they are the same.
Okay. So if I would like to, if, for example, hydrogen, if it's a helium atom, for example,
Yes, yes.
What about the energy? What is the energy, the equation? Is it the same?
It will be different. We will have different energy level diagram.
But how
Because
are you able to get the negative 3.4 EV?
in this case,
Yeah.
so n here is equal to 2. So 2 square is 13, which means it is 13.6 divided by 4.
Or
Yes, it
and you
it
get
is 3 point
negative,
something.
you get
This,
negative
yes.
3.4. Okay.
Yes.
So I think now it is degenerate because we only have one electron in hydrogen.
Yes.
But if we have more electrons,
More than.
so when electrons start filling up the orbitals, you have different energies in between
Yes,
2s and 2p.
yes. Yes.
Okay.
Thank you, Dr. Mark. I think I missed to mention something. This is the energy of orbital when the electron fills up the orbital. That's why, since we only have one electron, then we have this degeneracy. But we will see the difference with the more complex case later, like the helium case and also the hydrogen molecule ion.
Shall we continue?
Yes.
Is this okay with you?
Okay. Let us continue to the third part, which is the many electron system. So previously we deal with one electron system because the hydrogen atom has only one electron. Now we are moving to the helium atom case. The difference is in the helium case, we are now having 2 electrons, right? So it is slightly more complex, more complicated. So here we have nucleus A again, denoted by this red part, and then we have electron 1 and we have electron 2. And the distance between nucleus and electron 1 is Ra1. The one for electron 2 is Ra2. And the distance between these two electrons is R12 of electron 1 and electron 2. And again, as the one in hydrogen atom case, we write the Tc. This is the 3D case Tc. And it's slightly getting longer because of the 2 electron system. So let's break down this term. We have T01 and T02. This is similar to the case of hydrogen atom. These are the 1 electron kinetic operator for electron 1 and 1 electron kinetic operator for electron 2. And remember, this operator assume that the electrons is moving without interacting with other particles. So even though we have 2 electrons here, they do not know each other. So they just move independently. And then we have the VES for A1, the VES and the VES of A2, which means the nucleus generate a potential and it is felt by electron 1, and we denote it as VES A1. And if the one that feel is electron 2, we denote it as VES A2. And we already know the exact form, which is the same as in the hydrogen atom. And then here we have another term which is not exist in the case of hydrogen atom, which is V12, which is the potential representing the interaction between electron 1 and electron 2. And this interaction is very complex. It is consisted of the electrostatic interaction and then electrodynamics and also spin. So since among these three, we only know the exact form of this electrostatic potential, we don't know the electrodynamics and we don't know how is the form of the spin interaction. So we don't know the form of this electron-electron potential, this VEE. And that is our first problem. So we don't know the complete form of this electron-electron interaction. And then the next part is the psi, the portrait wave function. In the case of hydrogen atom, it only depends on R1. But now we have two electrons, so it depends on R1 and R2. So to construct this psi, we need to use the so-called Slater determinant. And you see this symbol again, it means you have to look it up by yourself. What is Slater determinant? So this is the example for this case. We have C1, psi1 R1, psi2 R2, minus C2, psi1 R2, and psi2 R1. C1 and C2 here is just a coefficient. Maybe you can imagine it as the amplitude of the wave function, just coefficient. And then psi1 R1 means the electron 1 in orbital 1. Psi2 R2 is electron 2 in orbital 2. Psi1 R2 is electron 2 in orbital 1. So it is like the opposite of the first term. And then psi2 R1, which is the electron 1 in orbital 2. So now our function here, the portrait wave function, becomes more complicated than the hydrogen atom case. And this portrait wave function, this psi, is 3 times q dimensional functions. Because, so here if we have 2 electrons, q here denotes the number of electrons. So if we have 2 electrons, then we have 2-dimensional functions. And if we have more electrons, it means we have more dimensional function. And it is a problem, right? Dealing with the 3-dimensional function is already not easy. And if we have higher dimensional functions, then the problems become more complicated. So the dimension of the function is our second problem. Remember, the first one is we don't know the exact form of this electron-electron potential. The second problem is the dimension of the function. But if we want to get the energy, the total energy, we have to put the certain conditions. In this case, we assume that the V12 as electrostatic potential because it is the only known form. So we define that V12 is equal to VES12, and then we assume that the state is the ground state. So the electrons occupy the 1s orbital. And then if we substitute everything and do the calculation, we'll get the ground state energy is minus 77.5 eV, which is 1.9% difference from the experimental observation. The experiment one is minus 79 eV. And we can guess that this error maybe comes from the simplification. Remember, in the kinetic part, we assume that the electron does not interact with each other, with other particle, and then we assume these interactions only happens via electrostatic interaction. So that simplification maybe is the reason why this error comes up. So now we take a look at the orbital energies, like the previous one. For in the case of hydrogen atom, we have minus 13.6 here for the 1s orbital. But for the helium atom, we have minus 24.5. And then there is something different here. For the 2 orbital, for the second orbital, in the case of the hydrogen atom, let us go back a bit here. So in the case of hydrogen atom, the energy, the orbital's energy of the 2s and 2p orbital degenerates. The orbitals is different, but the energy is the same, because in the case of hydrogen atom, it is only depends on n, while in the helium atom case, let's go back. Now the degeneracy is broken, And it is also observed in the case of n equal to 3. So in the case of helium atom, the energy is a functional of n of psi and L. Previously, it is only depends on n because it only have one electron. So now, the orbitals, they are no longer hydrogen atomic orbital, but it is hydrogen-like atomic orbital. And when electrons occupied more atomic orbital, then the orbital's order in energy is like this. So 1s, 2s, 2p, 3s, and so on until 5p. And remember that in this case, the energy is the functional of n and L, not only n as in the case of hydrogen atom. And then now let's move to the different case. This is similar, not really similar. Previously in the helium case, we have one nucleus but two electrons. Now we have the opposite. We have two nucleus and one electron, and the system is called as the hydrogen molecule ion. We have two nucleus here. We have nucleus A and nucleus B, and we have electron 1, the blue dots. And again, we try to write the T-say, the 3D T-say, which is shown like this. And we already know the T01, the VESA1, VESB1. This is owned by electron 1. So this is similar with the previous case. And now we have VAB, which is not appeared in the previous case. VAB is also nucleus B. And similar to the previous case, we don't exactly know what is the form of the potential, but what we only know is that's the electrostatic potential. So we use it. We use the electrostatic potential as this VAB. And then in this case, now we have another problem, which is since we have two nucleus and we believe that the nucleus are moving, so we have two nuclei, we believe that the nuclei is moving, and therefore the nuclei must also occupy this orbital, right? So the orbital, the psi is now as a function not only electron's position, but also the nucleus, the nuclei position. And this is another problem. So I repeat again, we have the third problem here, which is the moving nuclei. And the fourth problem here is the two-in-one body problem, which means the psi, it is not only depends on the position of electron, but also the nuclei. That's why it is called as two-in-one body. And that also improved the complexity of problem number 2. Remember, number 2 is the problem about the dimension of the psi. And then we also have the fifth problem, which is since we have two nucleus and both nucleus can generate a potential field, so that makes the system no longer a central force. So that increase the complexity of the system. And due to these 5 problems, we have the 5 problems that makes this 3D T-say, this many electron T-say is unsolvable. So now let us recap the 5 problems we have. The first problem, remember, we don't know the exact formula of the electron-electron interaction besides the VES is unknown. So the exact formula of VEE beside VES is unknown. It is our first problem. The second problem is that the second as well as the second prime, the psi is not only the position, the function of electron's position. This must be RE. There is a slightly typo here. This psi is not only depends on the position of electron, but also the nucleus. So it becomes 3 multiplied by P plus Q dimensional functions. P denotes the number of the nucleus and Q denotes the number of electron. So the higher the number of nucleus and also the electron, then we have higher dimensional functions, which is difficult to deal with. And then our third problem is that the nuclei, more than one nucleus, are moving. And then our fourth problem, we have 2 in one body, this psi. And our fifth problem is in the case of molecule, if we have more than one nucleus, then the potential fields are no longer central force. And since it is no longer central force, it is not like the case in the case of hydrogen atom. And solving that many electron thesis is impossible, said this guy. So this guy keeps appearing because Dr. Vera like this very much. Right, Dr. Vera? So remember these 5 problems. And then now, in the next part, we are going to talk about density functional, and it is still related to these 5 problems. So we have to memorize, just remember these 5 problems. Okay, so to solve that many body problems, we need a tools, and the tools is the many body quantum mechanics. So if we visualize it in a Venn diagram, this is the area of quantum mechanics. Then many body quantum mechanics is part of it, is part of the QM. And then we also have the Schrödinger equation, which is part of the quantum mechanics. And the thesis we discussed a lot before, it is also part of the Schrödinger equation. So if we try to use the many body QM to solve the 3D time-independent Schrödinger equation, it is represented by this shaded region, and can be written mathematically as this equation. So let's try to break down term by term. In the first term, we have the kinetic operator for nucleus. So the nucleus is moving, right? So we need the kinetic operator to measure the kinetic energy. And P here denotes the number of the nucleus. And then in second term, we have the kinetic operator for electron, summed over Q, in which the Q is the number of electron. And then we have the potential operator for nucleus-electron interaction, potential operator for nucleus-nucleus interaction, and the potential operator for electron-electron interaction. And then we have psi, which depends on the position of electron and nucleus, and it is equal to E multiplied by psi. So this is rather complex, but many body quantum mechanics provides the methods to simplify the many electron thesis. So this is many electron thesis, and now we are trying to simplify this so that we can get the solution. And that is why this program has 2 courses, and one of them is the many body quantum mechanics. And the most crucial simplification is the Born-Oppenheimer approximation. So what is Born-Oppenheimer approximation? The BOA, for the Born-Oppenheimer approximation, applied the adiabatic theory. And according to this theory, we can separate two in one body, becoming one body by fixing the position of the nuclei. And how we can apply this theory, it is based on the comparison of the mass of proton with respect to electron. So the mass of proton is very, very, very massive, right? It is even larger than 1,800 times the mass of electrons. So since proton is very, very, very massive compared to electron, we can think that the electron is fixed with respect to the electron. Sorry, the proton is fixed with respect to the electron. So, by relying on that approximation, now we can simplify this many electron thesis. So first, we can get rid of this kinetic operator energy, kinetic operator, because we assume that the nuclei is fixed. Since it is fixed, it does not move. And if it does not move, it doesn't have the kinetic energy, right? So we can get rid of this first term. And then these nucleus interactions, since we assume they are fixed, it means the potential energy among them, among the two nuclei, are constant. So instead of this operator, we can change it into this VR. This is energy, potential energy between nuclei as a constant. And then the third effect of this Born-Oppenheimer approximation is we can get rid the dependency of this psi to the nuclei position and change it into a parameter. So psi is no longer a function of nuclei position, but it is just governed by the parameter R. So instead of a variable here, it becomes a parameter. All right, so remember this is the summary of the 5 problems we talked before. First problem, we don't know the exact form of this VEE. And then the second problem is the high dimension.
Rizka-san,
Yes.
I think we need to have a break
Okay.
every point because a student need to reread and answer the exercise.
Okay. So maybe we take a break for 5 minutes.
All right, sure. Let's take
And
a break.
then, yeah, maybe I will review from this part again later.
Yeah,
So let's have a
because
break.
they need to take a note to answer the exercise.
Okay.
Your presentation is very interesting. I was actually, I want to listen more and more and more. I forgot about the exercises.
Oh, really? Sorry. I also forgot
I was
to
carried
stop.
away. I was carried away by your slide, your presentation. Very interesting. A lot of information. So okay, you guys have about 5 minutes. You can go through the questions and try to answer them. Okay.
Yes. I think some exercises also, some answers already mentioned during the presentation.
Yes.
So maybe they can write.
I think Dr. Febdian also joined this class.
Oh, Dr. Fentian?
Is he around?
No, I'm getting more nervous.
Yeah.
No worry. I think he's just listening, or maybe just switch on to view what is going on.
I see. I'll pretend that I did not hear what Dr. Nisa said.
Can you go back to the too many body problem?
Oh
Yes,
my,
Sensei.
teacher.
Sorry, I
Yeah.
cannot share my video because so many people around me.
Yes, Sensei. Which part, Sensei?
Back, 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 back. Yes, this one.
Mm.
So it is good to emphasize to students, two-in-one body. We have this in daily life. Like for example, we have shampoo, two-in-one, remember? Conditioner and shampoo, two-in-one shampoo. We cannot split them, right? If we have shampoo, two-in-one, conditioner and shampoo, two-in-one, in one box, we cannot split them, but we know there are two fluids inside the shampoo, one for the conditioner and the other for common shampoo. Two-in-one body in this case is exactly the same. We cannot split between electron and nucleus. In this case, nuclei. For atom, we can ignore the kinetic of nucleus. Do you know why? Because the central force. We say in the beginning, we don't care about nucleus. We only care that nucleus generates the central force, the potential, electrostatic potential. Remember? Because we don't consider the existence of nucleus. Can you go back to hydrogen atom?
Yes, Sensei.
Here, yes.
Oh, no.
This is helium.
Helium. This part.
Yes, this one. Because we do not consider that nucleus is there. There is no nucleus basically in T-cell. There is no nucleus. It is possible for electrons moving, for the electron moving, passing through the nucleus. So there is a possibility for electron is exactly in the position of nucleus. For example, 1s, orbital 1s, the 1s, right? Yes. Orbital 1s allows electron in the position of nucleus. Why? Because there is no nucleus according to this. Of course, it is not correct. It is one of the paradox actually. I hope you explain here in the paradox in TC for hydrogen.
Oh, yes.
Yeah, kinetic requires electron does not recognize nucleus.
Yes.
It is moving alone. But potential requires there is nucleus and there are standing still. Sorry, I cannot go longer because I have to continue my workshop here. Thank you very much, Rizka.
Yes,
Thank you, Dr. Mark and
Sensei.
Dr. Vera.
Thank you.
Yeah.
Thank you for coming in for a while.
Yeah, remember, two-in-one problem. We have it in daily life.
Yes, Sensei.
Okay, thank you.
Thank you, Bebdian Sensei.
Thank you.
Thank you.
Do we still have time for a break? I forgot to count.
Can we just give another about 2 minutes, 2 or 3 minutes?
Okay.
Okay, I'll be back.
Maybe I need to go to the restroom first, Dr. Vera. So I'll go maybe 3 minutes.
Okay. Okay, for the student, you can read the handout and also answer the exercise. So after the class, you can do your exercise and then submit to the e-learning.
I've arrived back, Dr.
Okay.
Mark and Dr. Kara. Sorry for waiting.
No worries, no worries, no worries. Yeah. Okay, you may begin and when you're
Okay.
ready.
Maybe I'll start from this part again.
Okay.
So remember, before we have the 5 problems before the Born-Oppenheimer approximation, our first problem is that we don't know the exact form of this electron-electron potential. And then we have a problem with the high dimensional function because it depends on the number of nucleus as well as electron. And then the next problem is we have the moving nuclei. And if when we have more than one nuclei, the potential is no longer a central field. And the last problem is that the 2-in-1 body problem, the thing that Fabian Sensei has just explained. We cannot split it. But after the Born-Oppenheimer approximation, now we can simplify, we can deal with the second problems. The three P plus Q dimensional functions now turn into 3Q dimensional functions because we assume that the nucleus is at fixed position. So it only depends on electron. And then since it is fixed, of course, it is not moving. So we have resting nuclei now. And then the central field, we still have the non-central field. And then the two in one body, now it becomes one body because we fix the position of the nucleus. So it only depends on the position of the electron. All right, so we deal with problem number 2, 3, and 5. And this number 5, since we fix the position of the nuclei and it becomes a parameter R. And yes, so these are, originally it is a variable because it can move, but now it becomes a parameter. And then regarding the resting nuclei, actually we have a problem here. So if we want to study the molecular vibration, for example, vibration between two atoms, we need the nuclei to move, right? But since we assume that the nuclei is rest, so we need another method if we want to study molecular vibration. And then still this electron-electron interaction still becomes a problem. Remember, we have a 1.9% error with respect to the experimental energy, ground state energy. So now we try to, so since we see that in this slide, we still have some problems, right? So now we want to simplify it further. And now we will try to move from the particles point of view to density. So suppose we have only one charge. So it is simple. We can denote it as Q1. And then if we have many charge, then we have Q1 until Q1, Q2, Q3 until QQ. So we have many discrete charges. And then if the charge is we have too many charge, we can also see it as a cloud of charge, which is the continuous charge. And we can take the dq and dq prime as the element of the charge. So we have three systems: single charge, discrete, and then many discrete charge, and we also can have a continuous charge. And then if we want to calculate the total charge for the single charge, it is very easy. The total charge is only Q1. And then if we want to calculate the total charge of this system, then we just need to sum over the first charge to the last charge. So just sum everything. But if we want to calculate the total charge of a continuous charge, now we cannot use the summation because now summation works for the discrete problem. For continuous problem, now we have this integral and this d tau. And what is the thing that we integrate? It is the density of the charge. So here we have discrete charge, and here in C, we have the density of the charge. Or just call it as rho. And if we want to represent this single charge, we can write it as a psi as a function of R1 because we only have one charge. It's rather simple, like in the case of hydrogen atom. But if we have many discrete charge, then our psi, remember this is the portrait of the wave function, then it is a function of the position of all charges. And if we use the density, which is actually the square of the psi, and then we integrate it over all the element of the charge. So this is the mathematical form of the density. Don't worry, don't be afraid with the mathematical representation. But the important point here is that if we use this psi, this particle point of view, then this psi R1 is a three-dimensional function. But if we make the case more complex, if we have many charges, now the psi becomes three q-dimensional functions. The larger the number of the q, the more complex the function we have. But if we use this density point of view, we will have three-dimensional function, whatever number the charge is. Why? Because we view it as one entity, as one cloud of charge. We do not count the discrete charges. We view it as a cloud of the charge. That's why we don't care with how many number of the charge in the cloud. We only see it as one entity, and that's why we have a three-dimensional functions. Not 3Q like this, just 3D. Whatever the number of the charge is. See, this is comparable to the case of one particle system, right? So the idea to simplify the things is to replace the wave function with the electron density. So instead of using psi, it's better to use the rho as function of R. Why? Because no matter how many electrons in the system, we only deal with the three-dimensional functions. And therefore, everything is now the functional of density. Remember, E, this energy is originally the functional of the portrait wave function, this psi. But now we replace this psi with the density rho. So our equation now becomes equation 4. And see, we get rid of the summation operator. Previously, we have summation operator. Now, in terms of rho, we don't have the summation operator. Why? Because we are only dealing with one particle system, which is one cloud of electrons. And as a consequence, Tc, this Tc as a function of rho is one electron Tc. And how to use rho in Tc? So to use it, we need to calculate the rho. And how to calculate the rho is just by using this equation number 5. It is proportional to the square of the portrait wave function of the psi. And then since rho is proportional to psi square, I will go back again. So this rho is proportional to this psi square, right, in equation 5. This is what I mean. It is nature to worry that there is a chance that two different psi lead to the same rho. For example, suppose I have rho is equal to 4. Then I can get rho equal to 4 both by take the square of +2 and also take the square of -2, right? So here 4 is the rho and 2 is the psi. So we can get 4 by taking the square of +2 or taking the square of -2. But we know that +2 is not equal to -2, right? So two different psi can lead to the same rho. But that was, and then Hohenberg-Kohn theorem deals with that. So here, the students can check this publication. This is the original paper. You can find it easily, I think. And then the Hohenberg-Kohn theorem ensure that there is only one psi leads to a unique row as long as the system is in the ground state. So the theorem ensures that there is only one possible psi that leads to unique row. It means if the psi is different, then the row is also different, as long as the system is in the ground state. Or mathematically, it is written in equation 6. We have psi GS. GS means ground state. It has a bijection with row 0. So the theorem ensures that only one possible psi in the ground state that leads to the row 0. And then the Hohenberg-Kohn theorem is also proving using the variational principle that the total energy given by rho 0, this rho 0, is the true ground state electronic energy, or EGS. So the earlier one I mentioned is the first Hohenberg-Kohn theorem, and the later part is the second Hohenberg-Kohn theorem. And both theorem leads to the density functional theory. So let's see this equation, this theorem a bit longer. We have two Hohenberg and Kohn theorem, which leads to the density functional theory, the theory that we use to do the calculation later. Okay, let us continue. And then among the energy component in equation 4, this is equation 4, we have T, VNE, and VEE, and all are as a function of density of rho. Only VNE depends on the position of the nuclei. It is clear because we have N. N stands for the nuclei. This one is the, T is the kinetic energy for electron, and this VEE is the potential of electron-electron interaction. So only the middle part depends on the position of the nuclei. And according to Born-Oppenheimer approximation, that approximation put the nuclei out of the system. So therefore, we can replace this V and E with V external, or denoted as VEXT, V external. And again, since we already move on from psi to, so since our psi is governed by the parameter R, so therefore our rho is also governed by parameter R. Parameter R, this big R. And remember, this big R is the nucleus position. And consequently, the nuclei position will determine the external potential and also the density. It will affect the density. But rho 0, the one, this one, I will go back again one part, this one, rho 0. But rho 0 is unique, and therefore there is only one possible R that can give rho 0. So if we have maybe some atoms, 3 atoms, for example, there is only one possible configuration of the atoms that can give the ground state rho, the rho 0. So mathematically, it can be represented by equation 7. So C psi in the ground state has the bijection with rho 0, and rho 0 has the bijection with the configuration of the nuclei, the R0. And this later part it is the basis of the geometry optimization. So there is if we get one possible R0, and then it will determine the rho 0, and it corresponds to the ground state C. So let's take a deep breath and resume again the 5 problems. Again, we have the 5 problems, and then the first simplification we made is after Born-Oppenheimer approximation. But for the first problem, the electron-electron interaction, we don't do anything with it, so it is still unknown. And then the 3p plus q dimensional function, it is reduced to 3q dimensional functions. So in Born-Oppenheimer approximation, remember, we assume the nuclei position is fixed, so we get rid of this p. And then the nuclei is assumed to be fixed, so it is resting. And then we don't do anything with the central field. And then we make the 2 in one body become one body problem by fixing the nuclei position. And then after the next simplification, the next approximation, the Hohenberg-Kohn theorem, still we don't know the first part. We don't know the electron-electron interaction form. But now we even reduce the dimension of the function becomes 3-dimensional function, whatever the system is. We don't care with the number of electron and the nuclei. The function will always 3-dimension. And then the nuclei become important parameter because it governs several things. And then still we do not do anything with central field. And then the psi, instead of psi, we take the square of the psi and it is proportional to the density. So now we use the density point of view. We don't view electrons individually, but we view it as a cloud of electrons instead. So up to now, we're still dealing with number 2, number 3, and number 5.
All right. So shall we take a break before you continue?
Okay. We
Yeah.
can have.
So after this
another-
will be, what is the next slide?
We still have
Okay.
how much time we have? 1 hour?
We have until 1 p.m. So it's Indonesian time is 12. We have until 12 p.m. Indonesian time.
Oh, we
Yes.
have
Yeah.
around 45 minutes.
Yes.
5 minutes.
Yeah. If you're able to finish early, then it's okay. No worries.
Okay.
Yeah.
So
Okay. Can we continue?
let's continue. Now we are arriving at the last menu before the closing. Let's resume again. After the Born-Oppenheimer approximation, we already simplified the 3p plus q dimensional TC into 3q dimensional TC. And then we assume the nuclei to be fixed, so it is resting nuclei. And then the 2 in one body problems become one body problem with R parameter. And then after the Hohenberg-Kohn theorem, we still don't know the electron-electron potential, the potential of the electron-electron interaction. We don't know the exact form. And then we have reduced the TC into 3-dimensional TC. And then we have important parameter R, which related to the nuclei. And then we still don't do anything with the central field yet. And then instead of psi, we are now using the rho, the density, which is proportional to the square of the psi. And Aksa said, we still don't know the form of this TC. So we will go deeper now about the density functional theory. So from the calculation of energy as a function of electron density, we have this equation. And then we can expand this equation into this line. So originally this T, we have one kinetic energy, this T rho, and then we split it into T0 plus T correction. So remember, we assume the kinetic operator energy as the one electron kinetic operator. That's and we know that in reality it should not be like that. So that's why we have to put T correction here. And then the V and E, now it is transformed to V external, governed by parameter R. And this electron-electron interaction potential, it is consisted of three terms, which is the VES, the V spin, and V correction. So any other thing which is outside this VES and V spin. And based on how the symbol is written, if we have the text in the upper side, it means that we don't know the exact formula. Sorry, if the text is on the upper side, already know the exact formula. So we know the formula of this T0 and then V external and VES. The rest, we don't know. And then we rearrange. So from here to here, we just rearrange. We collect the noun formula in the first three term, and the last term is the unknown formula. And then this unknown formula can be distributed into these two new terms, which is the V exchange and V correlation. And these two terms can be combined into one single term, which is VXC. So now we successfully reduce the number of the unknown functional formula from many to one, which is the VXC. However, the story does not end here. So although we have simplified from some terms into one unknown terms, but the story does not end. And then I ask Aksa again, how do we get the energy? And Aksa answered, if we know the density, of course. But we know that density is proportional to the square of the psi. True, Aksa said. That is why we have to find the psi first. And the question is how to find the psi? And Aksa answered, there is only one way to get the psi, which is solving the many electron thesis. And I was surprised because you said, Aksa said that there is no more thesis. But she answered that we have to get the psi from many electron thesis. Yes, there is no more thesis after this section. Aksa promised. See, it is Aksa who promised that. And remember, Aksa said, Allah is indeed with those who are patient. And you can find it in Al-Baqarah, verse 153. So, from the energy to Kunsham equations. And before that, you can check this reference. This is the paper about the Kunsham equation. And please download by yourself. And then now we have this equation. This 1, 2, 3 terms is one electron energy. It assumes a non-interacting system, like when I explained about the kinetic operator in the hydrogen atom case. Oh, sorry. And since we are dealing with non-interacting system, we also use the non-interacting density, which is the rho Ks. Ks here stands for the Kunsham. So this is rho Kunsham, which can be calculated from the square of this phi I. So if you are confused, we can compare it with the previous density we know before. In the previous density, we have rho and we have a psi square. But in this Kunsham density, we have this rho Ks. We have Ks, we don't have any letter here. And we have phi I instead of the psi. And this rho Ks is needed to calculate the Vxc, to determine the Vxc. And this equation can be simplified by gathering the potential term VES, V external, and Vxc as effective potential operator, or VF, V effective. And this T0, is the non-interacting kinetic operator. And of course, it is a function of rho Ks also. So now we can rewrite this equation in a simpler way, which is the one in the yellow box. So the equation in the yellow box is very important. This is the kinetic, non-interacting kinetic operator as a function of rho Ks plus the potential, effective potential as a function of rho Ks. And phi I is the orbital here. You see the Kunsham. It gives the Kunsham density. And then we have EI and phi I. So phi I is called as the Kunsham orbital. Index I means the ith orbital. And correspondingly, we have the energy, which is this epsilon I. This is Kunsham orbital, and this is the energy of the Kunsham orbital. And this is Kunsham equation. Right? This from energy to Kunsham equation. And this effective potential, now it behaves like a central force. So remember, previously we have the 5 problems. Let me remind you again. Where is the 5 problem? Here we have this 5 problem, and before we still not doing anything with the central field, right? But after in the Kunsham equation, this effective potential behaves like a central force. So now all the 5 problems are solved. And let's listen to Aksa's wisdom again about the Kunsham equation. So see here, guys, you see Aksa's hand. Aksa is offering something to you. She extends her hand and offer us with the Kunsham equation. So this is the Kunsham equation offered by Aksa. And below this one, in the upper side of Aksa's hand is the Kunsham equation, and in the below part of Aksa's hand is the legendary but scary Tc for hydrogen atom. Kunsham equation, and the lower part is the Tc of hydrogen atom. And if we compare them, it is similar, right? We have the non-interacting kinetic operator. We also have it in the hydrogen atom case. We have this V effective and we have this VES in the hydrogen case. We have phi and we have psi here. We have epsilon I and we have E here. But remember, the upper one is the Kunsham equation. The lower one is the Tc for the hydrogen atom case. And they are similar. This is our first important point. The similarity between Kunsham equation and the Tc for the hydrogen atom. And then this effective potential will be true if the Vxc form is known, and that governs that leads to the born of B3LYP. Maybe you ever heard this before, and also its friend, so some other functional exchange correlation functional. And then to determine Vxc, since it is a functional of rho, we need rho Ks. And to get rho Ks, we need phi I. And to have phi I, to get phi I, we have to solve the Kuhn-Sham equation. So this is like a loop. And to end the loop, we need a trial phi as the initial guess, right? And to do that, we need the basis set and multiplicity. Why we need multiplicity? Because phi is also a function of S, the spin. That's why we need multiplicity. So that is the third important point. Oh, I'm sorry, I missed the second important point. The second important point is the born of the B3LYP and its friend, which is the exchange correlation function. And the third important point is the basis set and the multiplicity. We need it as trial wave function. We need the trial wave function, we need the trial phi to end the loop, this loop. And then this psi behaves similarly with phi. And that's why this phi behaves similarly with this psi. So this phi is called as the hydrogen-like atomic orbital. And then another thing that we need, in addition to the trial phi, we need the V external. And we can get the V external if we have the information about the atoms, like oxygen, carbon, nitrogen, or etc. And then the position of the atom, and also the total charge of the system. And it is the fourth important point here. So before closing, I will repeat again. The first important point is that the Kuhn-Sham equation has the similar form with the hydrogen, the Schrödinger equation for the hydrogen atom. And then this V effective, we can get the true value if we know the exchange correlation. And that leads to the born of B3LYP and some other correlations. And then, but to get the Vxc, we need rho Ks. And rho Ks need phi I. And we need phi I to solve this equation. If we want to know phi I, we need to solve the equation. But to solve the equation, we need phi I again. So it is like a loop. So to end the loop, we need to provide two things. The first one is the trial phi, which is related to the basis set and the multiplicity. And the second thing is the external potential, which is related to the atoms, the position, and the total charge. So practically, when we do the simplest DFT calculation, we need to provide these things. So we need the basis set, multiplicity, and then the type of the atoms, the position, and also the total charge. And with this information, we can already perform the simple DFT calculations.
Okay.
So
is that the end?
yes, and then as the closing, Aksa will say wisdom again. We are done with the theories and equation that may turn your dream into nightmare. But it is all right if you do not understand everything at the moment, and we will understand them in practices with module. So you will surely come back to this file when practicing the module. Meanwhile, let us congratulate ourselves with a cup of coffee or maybe a cup of tea if you don't have coffee, and see you in the next meeting. So that's all from me, Dr. Mark.
Yes,
Thank you very much.
Thank you, Rizka, for a very wonderful presentation. Very clear and I think very precise with the whatever you have shown. We have also recorded this, and for our first meeting as well, I think that I haven't have you all uploaded the recording for the first meeting in e-learning?
I'm not sure, maybe
Fabiana? I'm not sure.
Fabriana?
I can't hear you.
Assistant,
Huh.
Fabriana.
Yes, Dr. Vera. I will try, but I'm not sure.
Okay. All right. So I think we will also upload this. Definitely we'll upload this for your reference. And for the next class, we will enter the computer lab. All right. For UTM students, it will be in computer lab 3 at C22. Okay. At 11 to 1 p.m. Malaysian time. Okay. We'll go through the slides and together we'll go through the modules. And I'm not sure, have we provided them the modules? Oh no, we haven't yet. So for my students, I will provide you the modules as soon as possible. And is there any other questions that you'd like to ask? All right. In the meantime, I think I've forgotten. You have to slide in. Please scan the QR code. Share the slides. Okay, is there anything else, Dr. Vera, would you like to add?
Yeah. Yeah, one of assistant already sent me the link of the video recording.
All right. So later I'll also try to upload it into the e-learning in UTM. Okay.
Okay. So maybe I will give you the link.
Okay. Sure. Is it saved in the cloud or the full recording you have?
In the Google Drive.
Okay. Okay. I think that's all for me. Okay, remember to submit the exercises, answer them, and to your respective e-learnings. Okay. So UTM student will submit to e-learning in UTM, and to the other students to your respective universities. Okay. So I think that's all from me.
Dr. Mark?
Yes.
I think I missed to stress one important point. Can I
Sure.
mention it again?
Yeah. You need to share your screen.
Yes. Can you see my screen?
Yes,
now?
I can see.
Okay, so yes, I think I need to stress a bit more about this row, this density. So we have two types here. This one, the right one is the ordinary density. But this one with Ks is the Kohn-Sham density. And this is the one that we used. So these two are different. This one is just ordinary density, and these are the Kohn-Sham density. And this Kohn-Sham density is the one we use in this Kunsham equation. So I just want to stress that because I'm afraid the students are confused because the symbol are rather similar. So yes, that part. I only want to stress that part. That's all from me, Dr. Bart.
All right, thank you.
Share.
Okay, I think that's all from me. Anything else from Fabiana? No?
No, Dr. Mark.
Okay, I think that's all. Thank you. Thank you all for attending the class. We'll see you next week. All right. Okay. Thank you.
Okay. Thank you, Dr. Mark.
Thank
All right. Thank you, Dr. Vera. Thank you, everyone.
Thank
you.
you,
All right.
Dr.
See
Mark,
you.
Dr. Farah, and students. See you in the next meeting.
Wait.
Yeah.
Oh, yes.
We need to take a photo.
Oh, really?
Oh.
Okay,
Take a
sure.
picture. So please open your camera.
Yes, please switch on your webcams.
Rico, please take picture of us.
Okay. Slide 1.
No, please make sure that everybody open the camera first. Then you take the picture. Okay, everybody ready? Okay. Please record.
Can I start the screenshot of screenshot?
Yes, please.
Okay. Slide 1. 1, 2, 3. Okay. Now slide 2. 1, 2, 3. And slide 3. 1, 2, 3. Alhamdulillah. Finish.
Okay. Thank you very much, Rico.
Okay, thank you.
Yeah, thank you, everybody.
Bye.
Thank you.
Bye.
Bye.